Hi, welcome back to our video series on all things math. This is the second part of a two-parter on calculus. Today, we're going to jump into the area of integration. Generally, integration is treated as the inverse of differentiation. Hence, why people also call them antiderivatives. This means to say, while differentiation calculates the slope of a function given the function itself, integration calculates the function from the slope. Integration can be expressed indefinitely as the integral of fx dx, or definitely as the integral of fx dx from n to m, where m and n are constants. Definite integrals calculate the area under the graph bounded by x equals to n and x equals to m, where n and m are the lower limit and upper limit of the integrals and the x-axis, fx. The result will be as a number representing the unit area under fx. For indefinite integrals, there's no such limit, meaning that the area under the graph is calculated and usually the result ends up as an equation with x. However, remember that integration is reverse derivation, which means when we differentiate a constant, it becomes zero. So there is possibility that the result of an indefinite integral has an arbitrary constant c. You might ask, what about definite integrals? Well, the way you calculate a definite integral is to calculate the indefinite integral at one point and obtain the result, say fx, and find the difference when x equals to m and x equals to n, or fm minus fn. As a result, the constant will simply disappear. To illustrate this, say you have a function fx equals to x and you are planning to integrate it. You need to consider what function could get you x after differentiation. This is something similar to division. When you divide m by n, you need to find the answer w such that n to the power of w equals to m. So now, let's take about 5 seconds to guess about what guesses an x after being differentiated. The answer is half x squared. When you differentiate x squared, you obtain 2x. But we only need half of the 2x to get the correct answer. That would mean we need to halve the original equation. Expressed in mathematical terms, this would mean fx dx equals to half x squared. Don't forget to add plus c at the end. We could have fx dx equals to half x squared plus c. If, for example, we wanted to calculate the area under a curve for a certain range, we would have fx dx equals to half b squared minus a squared plus c minus c. Having talked so much about integration, it might still be difficult for you to visualize what we are calculating during the process. As mentioned earlier, integration is obtaining the area under the graph. But how exactly do we achieve this? Well, let's say we are looking for the area under the graph of the following semicircle. The way how integration works is that it separates the area into very small rectangles with width dx. The length of these rectangles depends on fx. This would mean that the area of each rectangle would be fx dx. And adding these rectangles together would give us a total surface area under the graph. In other words, recall that integration is expressed in terms of integral fx dx. We can take the integral sign as the sum of the areas of all the rectangles, each one having area of fx dx. Relating this back to the idea of tiny nudges, we can approximate the area under the curve bound from a to b inclusive by using multiple tiny rectangles in that range. As a result, the area under the curve modeled by multiple tiny rectangles a will be equals to the summation of fx times dx. The smaller the width of the rectangle, or the more rectangles we use, the closer the approximate value of a to the actual area under the graph as shown in the picture. This sum of area a is also known as a Riemann sum. We can express dx of small nudges in x as b minus a over n, where n is the number of rectangles. We can rewrite the area under one curve as the sum of areas of all rectangles with length b minus a over n, multiplied by the value of f at that point. which we can surmise using this expression, a plus b minus a over n times I. Since we want to approximate the area over an increasingly large number of rectangles, for the sake of simplicity, express a plus b minus a over n times I as xi and b minus a over n as dx. Well, that's basically what we're going to cover in this video. I hope that this video can help you understand more about integration, what it is, and how it is useful in real life, and make you more integrated in mathematics. Don't forget to hit like and subscribe on your way out, and I will see you soon.